Okay. So anything that I can write as such will simplify this equation, and I'm allowed to do this operation because I have basically I can add any factor to any vector potential and it won't change the end result. So I may still have the same magnetic field. So for the simple case we have for BZ, okay, so I have a magnetic field, a uniform magnetic field pointing along the Z direction. There are various ways to write down a vector potential. So for instance, one of them would be something like this. Now I have to basically make sure that whatever I write here has to be equal to, so this product needs to be equal to some B magnitude times the Z hat direction. So the way I do this is I have X hat, Y hat, and Z hat, okay? And then I have derivative over X, derivative over Y, derivative over Z. Then I have my X component, Y component, and Z component. So to be able to find, for instance, the X component of this curl operation, what I do is I say, okay, I'm going to find out the X hat component. So what I will get is del Y AZ minus del Z AY. So this is the X component. What I do is, basically this is a determinant of this matrix, but the easier way to remember is if you're going to look at trying to find the X component, then you multiply or apply this operation to this one, and then this to this one, so you get a minus sign. So this is the X component. For the Y component, this time you focus here, so I have to do the operation like this, AZ minus del Y del Z AX, okay, so I use these guys now. And for the Z, I'm going to use the rest. So I will have something like this. Del Y del X AY, then minus del Y del Y AX. So the overall product, if I had a complicated vector that has components in X, Y, and Z directions, then my final product would be would contain X, Y, and Z in this form. So now for our simple case, let's try to find out what kind of a vector potential we may have. One option is this. So I'm going to only focus on the Z component, right? Del X AY minus del Y AX. So I can have my A vector to be AX, AY, Z. So this denotes the X hat component, Y hat component, and Z hat component. Okay, so obviously I don't need any Z component here. So one thing that I can do here is I can choose AX to be B times Y, and my AY to be 0. Let me put a minus sign here. So if I do this operation, my AY is 0, so this will be 0. Del Y acting on AX will give me, so del Y acting on minus BY will give me minus B. So overall, yes, so we have minus sign here as well. So my BZ hat is going to be Z hat. I have one minus sign here, one minus sign here is going to be this. So one choice of vector potential would be this. So my vector potential overall is minus B dot Y, 0, 0. So this is basically a vector field, just like our magnetic field. It's a uniform magnetic field pointing in the Z direction. So this vector potential is a uniform field pointing along the negative x direction, and it changes with y. So at y equals to 0, my vector potential is 0. As I increase the y, it linearly increases. So this is a rather abstract way of looking at magnetic fields. Unlike electrostatic potential or electrical potential, vector potential of magnetic field is more abstract, and it's rather difficult to find a physical meaning to this vector field. But as we'll see in a moment, it's deeply connected to the momentum that the electromagnetic field carries. So this is one way to write this vector potential, but it's not the only way. So I can show you another vector potential that can describe the same magnetic field. For instance, what I can do is now, rather than, let's see how to describe it. I can write down AX to be minus B half Y, okay? And my AY to be B half X. So if I take the derivative of this guy, I'm going to have B half, and then this will give me a minus B half, minus plus B half. So let me do the operation. So this is going to be B half X minus B half Y. Of course, I have the derivative here. Okay? So if you do this, you'll get B halves. So this will be total of B. It's in the Z hat direction, so it describes my potential. So my new vector field is basically this. So two different vector fields describing the same magnetic field. So remember this operation? I said if I add gradient of any scalar to my vector field, it will be, a different vector field describing the same magnetic field, so it wouldn't change my equations. And you can check that indeed this is true. So all I have to do is add the shift that's given by the scalar to my A0, which you could assume that this is our A0, and then you add this shift to A0, and you end up with this new A vector. Okay? Just for general information, this is called a gauge transformation. But you don't have to remember this. It's if you see it sometime later, you will remember what gauge transformation was. And it's quite useful to simplify the algebra of mathematical description of many systems. So, for instance, this is more complicated, as we'll see in the description of, in quantum mechanical description of a particle moving under the magnetic field. But when I make a transition to here, it becomes a much more simpler set of equations to solve. Okay, so we now got this one. Any questions regarding the vector potential? Any comments? Anything you would like to add? What's that? What is the question? Mm-hmm. Yeah. Mm-hmm. Yeah. Yeah, but it would be too much for those who see the vector potential for the first time in their lives. Yeah, but that's not important at the moment. All you have to know here is that we can describe magnetic field, which is basically a vector field, in terms of another vector field. Okay? And as we'll see in a moment, this vector field will be useful to describe momentum of a particle, a charged particle in an electromagnetic field. Okay? Too many fields. So now momentum of a charged particle moving in a magnetic field. Okay, so how is that different from a charged particle sitting without doing anything? So basically what I'm asking is, let's say I have an electron here, okay? And if I put another electron all of a sudden to this point, then there will be an attraction between these two, repulsion between these two electrons. Okay? And then this force, the Coulomb force, will result in change of momentum in these particles. So far, that's simple to understand. We are basically applying the Newton's third law, and it works just fine in this case. But what I'm asking is rather more complicated. I take an electron that's moving with velocity v, and that carries, of course, minus e charge. Now, what kind of a picture are we looking at here? First, it creates its own electric field, but unlike the static case, these electric field lines has to, I don't know, I mean, if you consider this instance and compare it to this instance, at that instance, the electromagnetic wave or the electric field lines are pointing straight out. And then if you trace, you will see that at every instance, the electric field lines move along with my charge. So when I look at the electric field lines at a far enough distance, I will not see the electric field created by my charge at that instance, but at an earlier time. It's like, you have to think it this way. I have waves, propagating, that is created by a moving object. Mechanical engineers will be very familiar with this one because, yes, Doppler effect. As this particle moves along with it, the wave fronts will be closer here, and then they will be further separated at the rear. Same thing, because the wave has a finite speed of propagation. It doesn't spread instantaneously. So what happens is that the electric field lines will start sort of bending backwards if you try to draw the picture. Of course, it's not a very accurate way to describe it. So that's one thing. We are not dealing with static fields anymore. The fields are now dynamic. Another thing is Ampere's law. Yes, I don't have a current, but I have a charge that moves in space. So in principle, I can define a current density here. So this moving charge will create its own magnetic field circulating around itself. Okay, so it will be like, it will propagate forwards and backwards, of course, but it will be like an envelope of magnetic field that's propagating with my charge. So all of a sudden, the problem is rather more complicated because I'm dealing with a moving electric field that's changing in space and time, and a magnetic field that's created by the electron itself. So this means, this whole thing means that some of the energy in this system is stored in the electromagnetic field. So some of the energy is stored in the electromagnetic field. Now, as a result, if there's some energy associated with the surrounding of this electron, so the fields around the electron, then there has to be a momentum that is associated with the electromagnetic field. So I'll try to actually demonstrate that indeed this is the case. Again, I don't expect you to follow all the algebra here, but what matters here is most is for you to understand that the total momentum that I'm going to write is the momentum of the mechanical motion, so the particle moving, plus the momentum of the electromagnetic wave. So the total momentum expression is very important. And you should be able to see where I'm going with this. If you remember, the Hamiltonian expression for the Schrodinger equation was this, right? So I had my Vx, and I applied this to a wave function to be able to find or to solve the Schrodinger equation. Now, in the previous case, I wasn't dealing with charged particles, so the only momentum that I had was the mechanical momentum. But now, the total momentum is what matters. So I have to take this electromagnetic momentum into account when I'm going to write the new Schrodinger equation. Okay? So let's write this. Now, work done on a charged particle. Let me start with this. Work done, I should say, by the electromagnetic field on a charged particle. So, what is work? It is the force dotted with, so let's say I would like to take my particle from here to here on a path like this. So at every moment, at every location, I can define this path as a vector, segments of vectors. You can think of this as I have my x and y directions, okay? And I can define this infinitesimal portion of the path in terms of infinitesimal vectors. So this will be x hat dx plus y hat dy of course, pointing as I move along the path. F will be pointing in different directions. So what I'm doing here is I'm trying to figure out the instantaneous work that is required to take my particle from this point to this point that is separated by a very small segment of path. Okay, so what I'll have is something like this. I'll switch back to Q for generic charge. Then I have the electric field and then V cross B. Okay, then I can write this dl as such. How fast my particle moves times the time interval it takes to go from here to there. Okay, so I described it in terms of a velocity. Then if you consider this part, V cross B dotted with V, you can show that this will give you a 0. So what we will end up with is E dot V dt. So this is the infinitesimal work. So I can write this expression as such. dV by dt, and then I will do an integration over a volume, as I'm going to write this as, so I have Q, velocity V, so if I integrate this over a volume of d tau, then I can write this as a J, current density, as I mentioned before. So E dot J integrated over this volume will give me the work done per unit time. It will become much more clear where I'm heading up with this in a moment. Now, for E dot J, I can write such an expression from the Maxwell's equations. So I have 1/2 del by del T, epsilon 0 E squared plus 1 over mu 0 B squared plus, sorry, minus 1 over mu 0 del dot E cross B. Okay, so if I take this into the integral, this is what I'm going to get. So for d, work done per unit time, minus d by dt, it's an integral over volume, 1/2 epsilon 0 E squared plus 1 over mu 0 B squared, integrate over this volume, then 1 over mu 0. Now I can change this over a surface integral by simply going from volume integration to a surface integration. So I get rid of this divergence. Okay. Now, I have two expressions here. One that is composed of the intensities of the electric and magnetic fields. And another is the cross product of electric and magnetic fields of this system. So the instantaneous work done on the system depends on the strength of the electric field and magnetic field. This guy here, 1 over mu 0 E cross B, is obviously a vector quantity, and it is named as, it's the pointing vector. Okay, and if you think about it, its physical meaning is something like this. It is the energy per unit time, per unit area transported by the electromagnetic fields. So I can write it as energy per unit time per unit area. Okay. Transported by the fields. What's that? Yes, this is Stokes' theorem that enabled me to write that. But again, the details of how I go from here to here is really not important. What matters is the parameters that goes into this whole expression. And I have to introduce the pointing vector because it's as it turns out, it's an important quantity. It's the energy basically transported by the fields. So now I can write down an expression for the momentum of the whole system. So if you look at the mechanical momentum, change of momentum, it turns out that it's something like this. D by dt, so rate of change of pointing vector integrated all over the volume. Then we have another term, okay, dot dA. So this is Maxwell's stress tensor. So this is basically, if you can think it as the force applied on the charged particle by the fields. The tensor is basically in case of 3 dimensions, it's a 3-dimensional object that describes each and every component along a certain direction. So, for instance, you can have components along x direction, xy direction, xz direction. So this object basically denotes, the tensor object denotes orientation of each object in certain directions, but that really doesn't matter. So this guy, you can see it as a black box, is the force that is acting on a charged particle because of the fields. You don't have to think the rest. So what I have here, if you like, this term is the, or I should say this term, this is the momentum in the electromagnetic field. Okay? Now, finally, I'm back at where I started. Let me write down the expression for a charged particle moving under the influence of an electromagnetic field. Now, the total momentum is given by mechanical momentum plus the electromagnetic momentum. And turns out that I have P, the mechanical part, plus the charge of the particle, of course this is a vector, times the vector potential to be the P total. Okay? And it's rather, I shouldn't say straightforward, but if you solve this expression, you can see that if you write this guy as E cross del cross A and do the algebra, you'll see that you end up with your total momentum expression as such for an electron. Okay? So this is for my electron moving under magnetic field. Okay? Any questions before we give her a break?
I think this proves to see the use of this formulas in some problems.
We will see it in a moment. The whole reason why I'm doing this exercise is to show how an electron moves, a quantum mechanical electron moves under the magnetic field. And this is actually a very important expression, and as we'll put it in the Schrodinger's equation, it will become more important because if you get this straight, you'll have no problem understanding quantum Hall effect. And we'll see Landau levels and other effects like the Haas-1 alpha and oscillations and so on. So we'll see their direct applications in real life scenarios. If you're talking about these parts, well, this is not too important for you. Just get the basics straight. I mean, of course, these are important equations that will eventually make you understand why we ended up there. But, I mean, again, the focus of this class is basically this part, not the rest. This is just to show you the path. Okay. Any other questions or comments? What's that? No. So from here to here, I mean, this integration to... Is it? Okay. Okay, it's a technicality that I forgot long time ago. So, who cares? Okay. Divergence theorem. Sorry, my bad. Okay, let's give a 10-minute break and then we'll continue. Mhm.
from this way.
Yeah.
So I know that when I came to that, we can interpret this because of impulsion.
Mhm.
Then we put magnetic field, the electrons fuse an impulsion, and
Mhm.
that impulsion can be related to the vector field A.
Mhm.
But I didn't know there is such a calculation that we can do this.
Yeah. Yeah. So that's I guess the main reason, the main physical reason behind why.
I have a proposal for exam.
Sure.
We should design two kinds of questions. One kind for
Sure. Okay. One without any physics in it, just math. The other is just physical interpretations. Sure. And there's so much like correlation between the math that we use in physics and the math used in engineering fields, because it's just using the same theorem, mathematical theorem, on different topics. So the only difference is the physical interpretation. So basically we end up with the same sets of equations. I think it's quite useful to gain an understanding of the real physical meanings or applications of these equation physics. So, but excuse me, but I can safely tell you that there won't be heavy calculations. So you'll rarely have to calculate things. I mean, of course there will be calculations, but I'll try to probe, how to say, more of a fundamental understanding of the subjects. So typically it requires minimal calculation, but a better insight about the topic. Okay. But again, the bottom line, you shouldn't worry about the midterm, please. Try to learn new things and try to relate these to your own research in one way or another. That's, I guess, more important. Okay, now we got the total momentum. So the first thing that I'll do is use a semi-classical approach to understand the motion of electrons in a solid. So from the simplified Boltzmann equation, this is what we got. Now, since I don't have the external electric field, this is the only force that an electron that moves at a certain velocity will feel. Okay. So what I'm going to do is this. My total magnetic field is E. I mean, it's already written there, plus, let me write it this way, H bar K. Okay, so let's see. Okay. Now I'm going to let's see. So what I would like to do is I would like to go from this vector potential to magnetic field, which is a quantity that I can physically measure and understand. So what I would like to do is figure out what this will give me. I've written it in a so complicated way that I am having trouble following where I started and where I ended. So let's do it this way. Let's integrate this P total over that line so that I can now, I'm going to have A dot dr plus, again, I'm going to use, so I have H bar K dot dr. Okay. So here I have, for this guy, I can write so I'll convert this to an integral over the surface that is bounded by this area, okay, which gives me the magnetic field. So this guy here is called the magnetic flux. Okay. Then I can do a similar trick to this guy. So I'm going to have, for instead of K, I'm going to have minus E over H bar d by dt R cross B. So for this expression, then I'll end up with something like this. Now again, I have to use the vector calculus. So minus E, then for here, I'm sorry, I have to get rid of this d over dt. This is time independent as before. So I can write H bar K as E R cross B. Okay. So this will directly go in here. So I have minus E integral R cross B dotted with dr. And by using the vector calculus, I can show that this is minus E B dot R cross dr. And this gives 2 times the area that is bounded by the line that I have chosen. So overall, this guy is minus 2E phi. Again, phi is the magnetic flux. So a magnetic flux is basically the, if you have an area that's enclosed by a certain line, and you have a magnetic field passing through this area, then the flux through this surface is given by B dot A, where A is the vector that denotes that surface. Okay, so this is the magnetic flux. So what I have here is now this expression, the total momentum integrated over that path is basically minus E phi, because I had, sorry, why do I keep writing Q? So this is E. So E phi plus minus 2 E phi will give me minus E phi. Okay, so the total momentum, in a way, integrated over this path is the electron's charge plus, sort of multiplied by the magnetic flux that is going through that area. Again, this is too abstract. Let's try to connect it to something more that we can relate to. Now, long time ago, we discussed Bohr's quantization. And the idea there was, I have an electron that goes around the circular orbit, just like this one. It goes around the circular orbit because of the magnetic field. Then we said, this orbit can only have integer multiples of the wavelength that I can, of course this is not correct, that I can fit in here. Right? So what I said is the angular momentum of this thing is quantized, where n is an integer number. And basically this quantization saved the hydrogen atom. But there's a backstory to this one. This comes from such a relation. So you have a momentum, and okay, your particle is taking a circular path along this line. So if you take this integral over that circular path, this line integral, then this Bohr Sommerfeld quantization tells us that you have to have n plus some phase, which is not important. So this is an integer. This is just some phase that is not too important for us. And then you will have h here, Planck's constant. Okay, so this is called Bohr-Sommerfeld quantization rule. And basically the idea that we applied in the hydrogen atom to quantize the orbitals basically stems from this rule. So a momentum that's integrated over a line around an orbit must follow such a rule. Otherwise, if you remember, we had de Broglie waves. Okay, you cannot meet the ends of the de Broglie wave in a periodic fashion. To be able to satisfy that the de Broglie wave end can meet in a continuous way, this condition has to be satisfied. Now, all of a sudden, we ended up with something extremely interesting. I have a charged particle that's doing a certain motion, so it has its kinetic energy, it's moving, and it turns out that now I take this part and gamma h and set it equal to the magnetic flux that I find, and all of a sudden this imposes a quantization on the magnetic flux. So I can write it this way. It's going to be h over E, which is a constant. This is Planck's constant. This is the electron's charge. Then I have n, which is an integer, and this is just a number. Okay? So it turns out that this, I can now put an integer index here. This is called the magnetic flux quantum. And the magnetic flux that is defined by the electron orbiting under the influence of a magnetic field can only define certain paths, if you like. It cannot take any path. It cannot assume any path it likes. So remember, this is magnetic field times the area. So when electron does a motion, it is doing a circular motion, the area defined by this motion, okay? I can continuously tune my magnetic field. But since this is quantized, it can only assume certain integer values, then this area, in a way, is quantized. It cannot take any area. It cannot define any area it likes. And this is not too crazy if you make an analogy between the hydrogen atom and this case. They are very similar scenarios, right? You have an electron that's orbiting around a charged particle under the influence of Coulomb attraction and the centrifugal force. It can only take certain orbitals. Now we apply the same logic to a charged particle moving under a magnetic field, and we ended up with a very similar result. It can only assume certain orbitals. And as we'll see, this has very interesting outcomes in solid-state physics. And we'll actually do a full quantum mechanical approach. This is still a semi-classical approach. We assume that this quantization out of nowhere based on the de Broglie waves, but we'll do a full quantum mechanical approach. But still, with this, we figured out that the magnetic field flux is quantized. And if you like, this guy is roughly 1 × 10⁻⁻15 Webers, which 1 Weber is Tesla square meters. Any questions? Again, the physical interpretation, is it clear? Come on, if it is not clear, let's discuss it. I have an electron that is moving with certain velocity. Then I have a magnetic field. So it has to do this circular motion because of the magnetic field. Even if you think it as a classical particle, that's the case. Then what I did is I figured out the total momentum that this particle carries. And then I wrote down the expressions. So this was the mechanical momentum that it will experience. And this is the momentum carried within the magnetic field itself, or the field that is generated by this particle. Then I have written down an expression for this line integral around the orbit, which has to follow this quantization rule. And eventually I ended up with this relation which tells me that the magnetic flux that goes through an area defined by the electron has to be quantized. And this is not crazy because there's de Broglie wave, this pilot wave following my electron, and I cannot take any orbitals. I have to meet the ends of my de Broglie wave, just like in the hydrogen atom. So it can only assume integer values of quantum flux. This is something that we can measure in metals. Why in metals? Yes, please. Mm-hmm. Yes.
But why do we define it that way? I mean, we normally know that the momentum of a particle is defined by its velocity times its mass. But here there is a variable.
That's only true for particles that are not charged. Yes. Because when you have a charged particle, that's what I try to explain actually with the figure, you have this electric field that's coming out of the charged particle. Also, as you move the particle, there will be an accompanying magnetic field created by this moving charge, because you have to follow the Ampere's law. You have a charge that's moving. So, right-hand rule, it will create a magnetic field around it. So all of a sudden, your moving charged particle creates its own electromagnetic field. And that electromagnetic field carries a momentum. So if you try to stop the particle, the price that you have to pay is not just the mechanical m times v. This is the price that you have to pay to stop the particle. So Newton's third law still applies, but you need to apply it to the field plus the mechanical motion. That's the way to look at it. I hope it's clear. It's rather complicated to understand, but this is how it really works. Any other questions or comments? Okay, so I hope this is clear. Now let's see. There's one more thing that I would like to do. Let me see. Where did I put that note? Okay. Let me get rid of this part. Okay, so let me explain what this is for, or write down what this is first. So this is oscillation of magnetic moment of a metal as a function of the static magnetic field intensity. Okay. So to be able to observe this effect, you need to go to low temperatures. You need a pure sample. And you need strong magnetic field. And this is purely a quantum mechanical effect. So let's try to explain what happens. Let me first solve the equations, and I'll explain what happens in the effect. So first, I'm going to, I need to work for, let's focus on a 2D free electron gas. Okay, so it's a two-dimensional gas that I'm going to focus on. I mean, I don't have to consider the third direction because my magnetic field points in a single direction. So all these interesting effects that I talk about will happen really in two-dimensional plane. So that's why I can safely ignore the second dimension. So what I'm going to do is this. A length that's defined in real space will be translated to a change in k value in the phase space. And the relation that I have is h bar over EB delta k. I mean, if you consider this, that's really the case. K h bar, so the expression that I have written here. So we had h bar k equals to E R B, right? So all I do is, if I change delta R, R by delta R, then this is the expression that I'm going to have. So if I define an area in the real space, then it will be mapped to a an area in the K space. So this S can be written as such. So the area in real space is going to be EB squared S. So basically I take square. So I define an area that's defined by delta R by delta R. So it will define an area by delta K by delta K. So I take square of both sides. I end up with an expression. So a real space that I define, A, an area, will correspond to S. Now, why am I doing this? So I can write something like this. B, my magnetic field, times the area that I define is the flux. Now I'd like to work with my quantum flux, or quantum of the flux, magnetic flux. Then I can replace this expression with h bar over EB squared S. So I would like to define an area in the K space that is also quantized. Okay? So this phi n will be equal to h bar squared E squared over B times S n. Okay? And then this must be equal to n plus gamma h over E. I guess I'm missing a minus sign. Okay? Now, let me write down the final expression for Sn. So Sn is n plus gamma minus E h b. So for any change, so this is basically, since we are looking at a metal, okay, the electrons. So let me draw this diagram. Again, this is the energy. So this is my Fermi level. And the electrons that can displace their K values are the electrons that are at the Fermi surface. Okay? So basically what I'm looking at is the change of momentum of the electrons at the Fermi surface. So when I apply this magnetic field, the motion of the electrons will be affected at the Fermi surface. So what this area is basically defined area on a Fermi surface. It doesn't matter how complicated it is, but it's defined in the phase space. Okay, so if you change the magnetic field, let's say you have a certain magnetic field that defines a certain area, and you change the magnetic field so the area that you define can change integer multiples of E over H. Now, what does that mean? When you take a metallic sample at low temperatures and have a pure specimen and have this strong magnetic field, what you will see is going to be something like this. If you try to measure the magnetic moment of the sample, so this is magnetic field and magnetic moment, will increase to a point and then all of a sudden the surface will be destroyed, and then it will decrease. And then you hit another n value, and then it will decrease. So it will give periodic oscillations based on the motion of the electrons that they can assume. So in a way, you destroy at certain points, electrons assume certain orbitals, and at some other scattering event becomes more dominant, they destroy their phases. So the magnetic moment of that metal starts oscillating with changing magnetic field. Since we are not, no single material is ideal, there will be broadening of this effect, but in the ideal case, there would be very well-defined spikes at certain magnetic field intensities. So that's one effect that we can talk about. But more importantly, now the next thing that I'm going to do is perhaps, let me see. Yeah.
Also, you can interpret this, like, for example, on the two-dimension,
Mm-hmm.
like n circle, each one is carrying like some one.
Exactly.
So if we add one more, then that is the Flux frequency.
Exactly. So I haven't written that down, so that's what I was thinking. So I should perhaps write it down. So, yes. Mm-hmm.
The S value is also changing, right?
Yeah. So the delta S, perhaps this is I should have written in the first place. Let's say I am looking at change from Sn and Sn minus 1. Then this change is going to be E over Hb. Okay? So, so the area change between successive orbits is given by E over H times B. No, just B. If you look at this expression, okay, so yeah, yeah. So this is it's any B, okay, just B. So now we can do one more thing. I don't know which one to erase. Let me get rid of this one. So I can do this. Now, if we ignore spin, a single orbital or single state, let's say I have a 2D gas that's confined in a size, box-sized L, will be given by 2 pi over L, okay, the area. So what I'm going to do is I would like to find the number of free orbitals that coalesce in a single magnetic level. So what I'm going to do is I'll divide this expression EB over H to each state that I have, which is 2 pi over L squared. So I'm dividing this area the change of area in my Fermi surface to each orbital to find the number of free orbitals that will coalesce into a single magnetic level. So this is what I'll get. My rho here is EL squared divided by H. Okay. So basically, each of these circular orbits, as I change the area like that, I'll find that, or I should say, as I change the intensity of the magnetic field, number of the free orbitals that will coalesce together will change. So in essence, what I'm doing is I'm taking my free electrons within the metal and then I confine them into very specific orbitals. This is another way to look at this, okay? I have a sea of electrons that I can treat as almost empty, or sorry, almost free. Then I apply this magnetic field, and then under the influence of this magnetic field, the energy bands, the allowed energy bands that I have here, they coalesce into orbitals, okay? They form certain energy levels because of the applied magnetic field. That's one way to see this. The better way to see this is a full quantum mechanical approach we'll do now. So I hope it will become much more apparent with this quantum mechanical treatment. Now I'm going to write down the Schrodinger equation. Again, if you consider Schrodinger equation, time-independent Schrodinger equation this way, this is called the Hamiltonian. And this operator in the previous case was something like this, right? So this part was derived from the fact that I have a kinetic energy plus the potential energy. But now I know that my total momentum is not just this mechanical momentum. So I have to write this down. My mechanical momentum plus the charge of the particle and the accompanying vector potential under the magnetic field. Okay, now I have basically this P plus E A squared over 2M plus V of X, and this whole thing acts on, well, I shouldn't say V of X, I should generalize now as I am working in 3 dimensions, and my wave function again is in 3 dimensions. Okay, now I'll do some algebra to figure out what's going on. So first of all, let me write down this expression, 1 over 2m p squared plus e p dot a plus e a dot p plus e squared and a squared. Sorry. I have r equals to e by r. Now, if you remember, we figured out the operator for the momentum. So it was h bar I del. So this guy, for those who needs refreshing of their memories, is basically this operation with a vector, okay? So when I take the square of this whole expression, or amplitude squared, so this is just the P operator, what I'm going to get is minus h bar squared. Now let me put this 2m here for the sake of making it look familiar. This. So this is the first term in my Schrodinger equation. Now plus E h bar over I del dot A, and then we must always keep in mind that I have this wave function, so I shouldn't ignore the wave function, okay, which is a scalar, so it can easily enter into this operation. Then plus, now this tricky part, that's why I didn't write this as 2EPA, because in quantum mechanics, the order where you have these operators really matters. So I'm going to have E A dot h bar over I that acts on, so I have my dot product here between A and that. And finally I'm going to have E A squared, and then again this will act on here. So I forgot to write 2 m's all over the place. So there will be divided by 2m. Sorry, thank you. Squared. And then this is equals to E phi r. Now let's focus on our case where we had our vector potential to be minus b y, sorry, x hat, right? If we go back to the case where I apply magnetic field, a uniform magnetic field along a surface. So basically this means that I really don't have to consider the z direction, because let's focus on 2D electron gas confined in 2 dimensions. So let's release the z direction, or let's confine the z direction and set our particles free in 2 dimensions. So what will happen is this. Let me write down a more simplified version of this equation. Minus h bar over 2m. Then I'm going to have derivative. This is now a function of x and y, plus del squared del y squared x and y, plus, now E h bar over 2m I. Now I have this product here. So my A is a vector along x direction, right? So this, only this will survive here, but my A is not a function of x, it's a function of y. So it will survive, so b y, but still that operator will act on this wave function. Okay, and it's x and y, sorry. Okay, I'm really running out of time, so I should better hurry up. So I'm done with this term. Let's move on to the next term. Plus E. Again, let me write down a minus here, because I'm going to write this guy 2mi. So only x component will survive here again. So I'm going to have del by del x phi xy. Okay. Sorry, let me get rid of this for now. So I'm done with this term, and this term. Now this is the simplest. E square. I have b squared, then y squared divided by 2m, and my wave function. And eventually this whole thing is equal to energy eigenvalue. All right, so this looks very complicated, but we'll simplify it in a moment. Now, as you can see, these...
Why is it subscript, right?
It's y, no, it's not subscript. It's y direction, actually.
Oh.
So you have to go back and change your whole... It's not a subscript, it's the y direction. Yes. So it will become very clear all in a moment. So this guy and this guy, they are identical. So I can combine my expressions. So let me go back to, or let's okay. Let me. Well, I won't be able to do it. Okay, so it's y plus del y squared plus this guy plus minus e h bar b y divided by 2, sorry, I don't have 2 anymore, m I del by del x psi xy plus e squared b squared y squared, or 2m psi xy equals to e psi xy. Okay, so still it looks very complicated, but now there's one more trick in my sleeve that I can pull off. Now, if you look at the equation, the potential acting on my wave function is along the y direction. Okay? So I can safely say that my particle, my 2D electron gas, is free in the x direction. So how do we treat free particles in x direction? We define a momentum to it, and we say it's a plane wave. So I can write down the wave function, this wave function, as some e to the ikx x times a wave function in y. Is this clear? I have a 2D electron gas. Under normal circumstances, it's free in 2 dimensions and confined in the 3rd dimension. So I'm looking at, I'm solving the Schrodinger equation in 2 dimensions, since my force is only acting along the y direction. Okay? So what I'm saying is, okay, my electron is still free in x direction, so I can take it as a plane wave. And the other function, I don't know its form, that I have to solve. So if you plug this in to this equation, this is what we'll end up with. And you will see that actually both sides will happily solve out. So I'm going to have minus h bar squared kx squared because of the second derivative divided by 2m, and I'll have the function itself. So I take, I think I'm going to have a plus sign here, right? It will give me a minus sign, so I'll have a positive sign there. Then plus I'll still keep this guy. Now I'll use double primes for second derivatives, because it's now obvious that I'm taking derivative with respect to y. then minus E h bar b y, first derivative with respect to x, I will have a kx coming from here and I coming from here, which will cancel out with this one. So I'm going to have e kx x and then y plus e square b square y square over 2m e to the I k x x y, which is equal to e to the I k x y. So all these I k x's can go away. I don't care. It's just a phase factor. Now the final equation that I ended up with is something like this. I have y double prime. Sorry, I forgot to write down minus h bar over 2 minus h bar squared over 2m here. So minus h bar squared over 2m y double prime. Then I have a function of y here and y squared here. So let me write it this way. I think I should refer to my notes to save us from some trouble. Well, I cannot find my notes. Let me take it from the book then. So, oh, this is quite different, but okay. Then I have h bar squared kx squared divided by 2m y plus, sorry, minus h bar kx eby divided by m and then y plus e squared b squared y squared divided by 2m y equals to e y. So I went over time, but for the trained eyes, actually this is the Schrodinger equation for a simple harmonic oscillator, which is basically a pendulum with a ball attached to it, and then at relatively small angles, the equation of motion, if you solve this system quantum mechanically, follows the same formula. In the next lecture, I'll make it more apparent, and then we'll solve the Schrodinger's equation, and we'll look at the outcomes of the Schrodinger equation, and we'll see that these are the energy levels, the orbitals that we will get are of a central importance to mesoscopic physics and solid-state physics, modern solid-state physics. So let's end it here, and on Thursday, don't forget the midterm, and well, let's not include this part in the exam. This is too fresh. And until the previous lecture, the Hall effect will be included, but not the quantum treatment of a charged particle moving under a magnetic field. Okay. So you can come to my office anytime you like to ask questions. Don't be shy. And you can always email me. Okay. And try to learn. Really, don't stress out yourselves too much. Okay. All right. See you on Thursday.